If I told you we just teleported something across the lab, you'd picture a shimmer, a vanishing act, a sci-fi tunnel. But listen, right now, in this room, we're watching a state leave one photon and arrive in another, without anything physical traveling between them. So what actually moved? And if we can move a state, what does that mean for a person? It's late. The kind of late where fluorescent lights feel like they're humming directly inside your skull. The lab smells faintly of warm electronics and cold metal. There's a fiber spool on the table, kilometers of glass thread coiled like a sleeping snake. On a monitor, a live plot jitters with statistical noise. On another, time tags scroll, nanosecond stamps, like the universe's own receipts. And the sound, if you've never stood next to photon counters, you should know, it isn't a dramatic thunderclap. It's a dry, metronomic clicking, a tiny insistence that something real is happening even when you can't see it. You're on shift with me. We're not reading history. We're inside it, waiting for a coincidence peak to rise above the background like a mountain out of fog. Somewhere in these clicks is a word people think they already understand: teleportation. So let's start with the only question that matters, the human one, the one hiding underneath all the equations. If you could relocate perfectly, what would travel? Your body, every atom? Your mind, every memory? Or just a description, a pattern, a recipe that can be rebuilt somewhere else? And if the destination copy is exact down to the last twitch of a synapse, does you continue? Or do you end and a twin begins? Before we go any further, I'm going to set rules for this audit. Because the single biggest way people get misled by quantum teleportation is by letting one word blur three separate ledgers. Here are the three things we will track separately, relentlessly, even when it ruins a good story. 1. Matter and energy. Stuff. Particles. Calories. Heat. Anything you could, in principle, put on a scale. 2. Information. Not mystical information, practical information. The minimum description needed to predict outcomes. The what that makes a system behave the way it does. 3. Identity and continuity. The part that hurts to talk about. The part physics can brush up against, but not certify from the inside. And here's the promise: quantum teleportation is not a magical tunnel. It's a protocol. A choreography. A sequence of legal moves that uses entanglement, an ordinary communication, to transfer an unknown quantum state from one system to another. The twist, the reason it works at all, is that quantum information can't be copied. Teleportation succeeds because the universe forbids cloning. Now, before the lab plot convinces you of anything, what is it we're even teleporting? What is a quantum state? If you've heard the phrase and it feels like fog, I want you to replace it with something you can hold in your mind. A quantum state is a compressed description of what outcomes the universe will allow, and with what probabilities. Not a single outcome. Not a hidden sticker that says, "This particle is definitely this." It's more like a rulebook, an instruction manual the universe consults when it decides what you'll see when you ask a question in the form of a measurement. Imagine you're holding a strange coin. Not a normal coin, this one doesn't have fixed heads or tails when you're not looking. Instead, it has a rulebook that says, "If you check me in this way, I'll give heads 70% of the time and tails 30%. But if you check me in a different way, the statistics change." A quantum state is that rulebook. It's a compact encoding of how reality will answer different questions. And here's the thing that makes teleportation feel like sorcery. We're going to transfer that rulebook from one physical system to another, without learning what's inside the rulebook. If that sentence makes you want to object, good. Keep that objection. Hold it like a tool. Because the first time you really understand quantum teleportation, you don't feel satisfied. You feel cornered, in the best way, by the bookkeeping. So let's build the stage. We need entanglement. And I want to define entanglement without turning it into a cartoon. Entanglement is not a signal. It is not a rope connecting particles. It is not a whisper traveling faster than light. Entanglement is a shared constraint. A single joint state spread across distance, describing two systems as one combined object in the language of probabilities. Picture two gloves in two boxes, left and right, shipped to two cities. You open your box and learn you have the left glove, so you instantly know the other city has the right glove. That's correlation, but it's not entanglement, because the gloves had definite handedness all along. Entanglement is stranger. It's like the boxes contain something that isn't a left glove or a right glove until you open one box, and yet when you do, the outcomes line up in a way no classical prepackaged story can explain. The joint rulebook is real, but the individual rulebooks aren't independent. In the lab, we manufacture that shared rulebook. We take a source, often a nonlinear crystal, and we pump it with light. Out of that comes a pair of photons whose polarizations are entangled. Call them A and B. A stays here near us. B leaves. It travels through fiber, maybe across campus, maybe across a city, maybe, if you're ambitious, toward a satellite link. But for our story tonight, B is simply far away. So we have our entangled pair, A here, B there. Now we introduce the unknown. A third photon, X, arrives with a polarization state we do not know. Maybe it's prepared by a separate device. Maybe it's the output of an earlier experiment. The key is, we treat X as a black box. It's in some quantum state, some rulebook, unknown to us. Here's the challenge. We want the photon at the remote station, photon B, to end up in exactly the same polarization state as photon X. Not approximately. Exactly, within the error bars of the lab. And we want to do it without sending photon X across the distance. Because if we just put X in the fiber and transmit it, that's not teleportation, that's delivery. So what do? We bring X next day, right here on the optical table. Mirrors. Beam splitters. Wave plates. The kind of fragile geometry where a fingertip's worth of vibration can ruin your night. We align the paths until X and A arrive at the same device at the same time, within a fraction of a wavelength. And then we do the heart of the protocol, a joint measurement on X and A. It's called a Bell measurement. Let me translate that. Instead of measuring X alone and A alone, we measure them together in a basis that asks, what kind of entangled relationship do these two have right now? This is the moment most popular explanations skate past, because it feels too technical. Don't let them. This is where the magic is either real or fake. We perform that joint measurement. The detectors click. 2 channels fire. A coincidence pattern. The experiment doesn't shout, it whispers. But the whisper is unambiguous. The joint measurement yields one of 4 possible outcomes. And we can label those outcomes with 2 ordinary classical bits. 0, 0, 0, 1, 10, 11. 2 bits. That's it. Not a library. Not a scan of a photon. 2 bits. Now we do something aggressively unromantic. We send those 2 bits to the location of photon B through an ordinary classical channel. A wire. A radio link. The internet. A flashlight blinking Morse code if you're feeling theatrical. The speed limit is the same as always, no faster than light. At the remote station, someone is waiting with photon B. They receive the 2 bits. Those bits tell them which one of 4 simple corrections to apply to B. Think of them as tiny rotations of its polarization, like turning a compass needle by a known amount. They apply the correction. And then, only then, photon B is in the exact state that photon X was in. If you're watching the plot with me, this is the moment you feel the vertigo. Because the data tells a story that sounds impossible in plain language. The state of X has appeared at B, at a distance, even though X never went there. Now, audit conclusion number 1, and I need it to land with absolute clarity. Nothing physical jumped from X to B. The particle at B was already sitting there the whole time. Matter didn't teleport. Energy didn't teleport. No photon vanished here and reappeared there. What changed was the state, the rulebook, associated with the photon that was already there, after we consumed entanglement and used classical communication. And audit conclusion number 2, the speed is limited by the classical bits. No faster-than-light teleportation. If the remote station hasn't received those 2 bits yet, they do not have the state. For you. They can't use it. They can't predictably reconstruct it. They can't even verify it in a way that gives them an advantage over light-speed communication. So if your mind is trying to picture a ghostly essence racing ahead of the bits, stop. That picture will betray you. But now we're at the edge of understanding, where the protocol is clear but the intuition starts to wobble. Because in the lab, when you line up the timestamps, it can look like the distant photon already had the state, in some sense, before the bits arrived. The correlations are sitting there, latent. The entanglement is waiting like a loaded spring. So you find yourself asking, almost involuntarily, where was the state before the bits arrived? This is where the universe forces us to be precise about what a state is. If you treat the state like a little object that must be located somewhere at each moment, you'll end up demanding superliminal travel. You'll end up inventing hidden carriers. But quantum theory refuses that framing. The state is not a marble rolling through space. It's a predictive object, an encoding of constraints and probabilities. And those constraints can be distributed across space in entanglement. Let's stress test our reality model with a thought experiment. You're at the remote station with photon B. You do not yet have the 2 classical bits. You decide to measure B in some polarization basis and write down the result. Can you extract the unknown state of X from B alone? No. Your outcomes look random. They do not reveal the rulebook you want. Now, after the bits arrive, you can take your earlier measurement record and compare it with the sender's record. Suddenly, patterns emerge. Correlations snap into focus. But notice what happened. Nothing you did locally gave you an actionable faster-than-light message. The meaning of your local outcomes depended on information arriving at light speed. So where was the state? It wasn't in B in the usable sense. It wasn't traveling through space like a courier. It was in the joint resource, the entanglement plus the pending classical information. And now we meet the hidden bouncer at the door, the law that quietly makes teleportation possible, the no-cloning theorem. Here's the metaphor first. In classical life, information copies like gossip. You tell one friend, now 2 people know. You tell 10 friends, now the rumor exists in 10 places without disappearing from yours. Quantum information doesn't behave like gossip. It behaves like a unique key cut from a material that shatters if you try to duplicate it. The act of copying requires you to look too closely, and looking changes the thing. More rigorously, if you have an unknown quantum state, there is no universal machine that can take that state and a blank system and output 2 perfect copies for all possible input states. The math isn't a preference, it's a contradiction if you assume copying is possible. Quantum evolution is linear, and perfect cloning would break that linearity. Now watch what that means for teleportation. When we perform the Bell measurement on X and A, we are not gently reading X. We are entangling X with A and then measuring the pair in a way that irreversibly projects them into one of the Bell outcomes. In plain terms, the original state on X is destroyed as an independent object. It does not remain intact here while also appearing there. You don't get 2 copies. You get 1 continuation at a new location. If that makes you uneasy, good. That discomfort is the honest signal that you're tracking the right ledger now, identity and continuity, not just particles and signals. So what actually moves in the protocol? Let's name it cleanly, without myth. First, entanglement is a resource that gets spent. We start with an entangled pair, a kind of pre-established joint rulebook. After teleportation, that entanglement is consumed. You don't get to reuse it. In practice, you must generate fresh entanglement for every teleportation event, like spending a one-time token. Second, 2 classical bits move through ordinary space, limited by ordinary causality. Third, the identity of the quantum state, the pattern that makes measurement outcomes come out with particular probabilities, is reinstantiated at the destination, conditioned on those bits. Now we have to confront the question people bring to this topic like a secret hope. Could you teleport a person? If you're expecting me to slam the door with a smug, "No, I won't." Not because it's plausible in practice, it isn't, but because the real reason is more profound than the tech isn't there yet. The reason is that once you understand the protocol, the question changes. It stops being, "Can we do it?" and becomes, "What would it even mean?" Let's do the physics first. A human body is around 10 to the power of 28 particles. That's a 1 followed by 28 zeros. And those particles aren't sitting quietly in isolation like photons on an optical bench. They're bathed in thermal noise, bombarded by air molecules, coupled to electromagnetic fields, exchanging photons with the environment constantly. The quantum state of U is not a neat vector in a textbook. It's a living, seething, astronomically complex state of a system that is continuously decohering, continuously leaking its quantum phases into the world. Decoherence is another word we should translate. Think of a quantum state like a perfect chord played on a piano. The precise phase relationships between notes matter. Decoherence is what happens when the room fills with echoes, conversations, and random vibrations until the chord's delicate structure is smeared into noise. The music doesn't vanish, but the special quantum coherence, the part you need for teleportation protocols, is lost into the environment. To teleport a human in the strict quantum sense, you need an entangled partner system of comparable complexity waiting at the destination, another 10-28 particle system, entangled with you in just the right way, and shielded from decoherence long enough to matter. Then you need to perform a measurement that effectively captures the full joint quantum state information needed for the protocol. Not just where your atoms are, but the quantum correlations among them. And here's the brutal bookkeeping. The amount of entanglement required scales with the amount of quantum information you're transferring. For 1 qubit, you need 1 entangled pair. For n qubits, you need n entangled pairs. A human is not n qubits in any clean count, but the sheer dimensionality involved is beyond astronomical. It's beyond the kind of number your brain can emotionally digest. Even if we grant impossible engineering, perfect isolation, perfect control, perfect measurement, there's still the protocol's logic. The Bell measurement destroys the original state. That's not an accident. That's the no-cloning theorem enforcing a kind of conservation law. You can move the state, but you can't keep it and also have it elsewhere. So, teleporting you would not be like stepping into a booth and stepping out unchanged, while your original self walks away whistling. It would be more like disassembling the original informational pattern as part of the act of transfer. Whether that counts as travel or as death with reconstruction is not something physics can answer from the inside. Physics can certify operational sameness. The destination behaves the same, remembers the same, speaks with the same cadence, flinches at the same childhood memory. Physics cannot certify subjective continuity, the felt threat of being the one who wakes up. And this is where many explanations get sentimental or evasive. We won't. We'll be humane and precise. The ethical question isn't a footnote. It's the natural consequence of taking the protocol seriously. If you build a machine that transfers patterns with deletion, you have built a machine that forces society to define what it values: the pattern, the substrate, or the continuity of experience. Now, right here, in the middle of the lab noise, with the detectors still clicking, I want to give you the eureka moment in the cleanest possible sentence. Quantum teleportation is best understood as state transfer with deletion, not object transport. The word teleportation is the misleading part. It drags in imagery from science fiction, tunnels, beams, vanishing bodies. The actual phenomenon is more elegant, and in a way, more unsettling. The universe allows the perfect transfer of an unknown rulebook from one system to another using entanglement, but it demands a price. The price is that the original copy cannot remain. So what does this imply about reality? Let's widen the lens without losing the human scale. Quantum physics treats the state as something real enough to do work. It predicts outcomes with ridiculous accuracy. It tells you how to build lasers and MRI machines and transistors. But it's not a thing you can point to moving through space like a billiard ball. It's closer to a compact set of constraints that governs what can happen when systems interact. In classical physics, locality feels straightforward. Objects influence nearby objects through forces, and signals travel through space. Quantum physics keeps locality for matter and signals. No usable faster-than-light messaging, but it allows correlations that are non-local. The universe is stitched together not just by what's where, but by joint constraints across what can happen. Entanglement is the cleanest example of that stitching. It's as if reality has seams that don't align with geography. Not because information is racing across the gap, but because the joint rulebook was never separable into two independent local rulebooks to begin with. Now bring it back down to your life, because this is where the topic stops being a party trick and turns into a mirror. You are not merely a collection of atoms. Those atoms are replaced over time, slowly, continuously, without you noticing. The iron in your blood, the calcium in your bones, the carbon in your cells, much of it cycles in and out. Yet you feel continuous. You feel like you persist. Teleportation, audited honestly, doesn't promise a Star Trek beam. It exposes something deeper. If the pattern is preserved and the original is erased, what do we mean by the same? Physics can give you a certificate that the operational pattern matches. It can tell you the destination photon behaves as if it were the source photon's state. It can tell you the statistics line up, the interference fringes return, the fidelity clears the classical limit. But the felt continuity, the I, is not a variable in the equations. So here's a contemplative thought experiment to carry with you. Imagine a future where you could teleport your entire brain state with perfect fidelity, with deletion at the source as the protocol demands. You step into the machine. You know the rules. The destination version of you will wake up and remember making this decision. The question isn't, would the world consider it you? The question is, would you step in, knowing that from the outside it looks like travel, but from the inside, you don't get to report what it felt like to become the continuation? And now the next great question, the one that opens the next door. If the universe lets us move a quantum state only by spending entanglement and paying the no-cloning price, what else is entanglement good for? Is it merely a weird correlation, or is it a foundational resource, like energy, that sets limits on what reality can compute, what reality can know, and what reality can become? If you want the full audit with the step-by-step protocol diagram, the intuition behind the no-cloning proof, and the exact reason those two classical bits are the speed limit, stay with this series. Subscribe not for hype, but so you don't miss the next time we take a famous word and separate the myth from the mechanism. And when the end screen appears, click the next video there, keep the thread going while it's still warm in your mind. One question for you, and I want a simple, honest answer in the comments. If a perfect copy of you appears elsewhere, and the original is erased, do you call that travel, or do you call it replacement?